All right, let's look at the examples. We'll start with ones that we really actually have seen. If alpha, remember we're looking at phi1 of alpha comma omega naught. That's how we're creating beta. If alpha is actually just an integer, then beta is phi1 of k omega naught. We extract the k and we do a g on it, but that doesn't do anything. And so it's just k. Okay, so let's run through these slowly and explicitly because it's nice and instructive just to take some baby steps here. Okay, if k equals 0, then beta is just the absolute simplest thing we can do to omega naught, take its successor, and the claim is that g sub omega naught plus 1 of x is equal to f naught of x. Well, yeah, we've known that for a while. G sub omega naught plus 1 of x, it's pretty easy from the basic definition of the slow growing hierarchy that is just x plus 1. Oh, yeah, you bet. That's the successor function. Okay, so I don't know if we ever really noticed that identification, but that's the absolute simplest example of a g using an infinite ordinal identified exactly with an f using the smallest number we know of, which is 0. Okay. So we've known that, but we haven't emphasized it before. K equals 1, okay, so we create beta out of phi1 of 1 omega naught. That's omega naught doubled. Okay, a calculation we could have done a long time ago is g using omega naught doubled of x is x times 2. It's an easy application of the ideas of the slow growing hierarchy. And again, well, yeah, x times 2. Hey, that sounds like f1 of x. Okay, not a big surprise, but maybe not something we've emphasized before. Notice that we don't have to do anything clever yet with tree ordinals. The fundamental sequence pretty much everybody would describe for omega naught plus 1. Well, actually that's not even a limit ordinal, that's a successor. But the fundamental sequence everybody would describe for omega naught times 2 exactly gives this answer for the g. Okay. K equals 2, though, it gets more interesting. Phi1 of 2 omega naught, remember, is omega naught times 2 to the omega naught. Okay. And the g function applied to that of x, if you unpack that carefully, it's x times 2 to the x. And this is where we really are using the fact that the fundamental sequence for omega naught times 2 to the omega naught involves powers of 2. Okay, and guess what? X times 2 to the x is the definition of f2 of x. Okay, so basically it's something we've seen before. We saw that when the g functions, when the argument of the g function, the ordinal argument of the g function is some piece of ordinary arithmetic applied to omega, and we apply that function, that version of the g function to x, we exactly get that same arithmetic just applied to x. Now, if, and so we hadn't sort of taken advantage of that quite so systematically before. So here we're not just doing some random piece of ordinary arithmetic applied to omega naught, we're actually applying f2 itself, the x times 2 to the x function, to omega naught. And voila, we get f2 of x. So we could have really seen this level of it before from that observation that if we do ordinary arithmetic to omega, it's replicated in terms of what we do to the numbers. And then we could have just chosen, hey, why don't we actually use f2 as the arithmetic we're doing instead of things like double ups or triple ups or things like that. Okay, something I didn't realize at the time, but this is going to make it very, very systematic. Okay, k equals 3. Okay, that's where beta is phi1 of 3 omega naught. Okay, so this is the one where it's hard to just write down explicitly what this is as a very precise tree ordinal. But what do we know? Okay, we know that g sub beta of x, g of this getting fairly big countable ordinal applied to x, that's the same thing as f sub 3. Okay, so this is where even the g of x, slow growing function, becomes respectable. F3 is on a double up level. Okay, so this makes more precise something we had observed before in some other videos as I was starting to talk about the slow growing hierarchy and leading up to the ordinal collapse stuff. I've talked about how already I've talked about how the ordinal height of this particular beta, is epsilon naught. Okay, and f sub 3, because it's iterated exponentiation, it's something on the order of 2 double up x, or maybe call it x double up x. And we had seen this before. A while ago, we had the approximation that if you take the slow growing hierarchy, but you look at the version of it with epsilon naught, a not so small ordinal, you actually start getting a function that's decently big, which is a double up, basically. Okay, and we have now been able to take that approximately equal and get rid of it, and have something where we've found a way to create a beta, a very specifically engineered beta, that was basically constructed out of a generalization of the fast-growing hierarchy, but applied to omega naught instead of to ordinary integers. And that beta gives you a g beta function that exactly matches F3 on the nose. Okay, and so that's the start. That's where this story gets not trivial, and gives us a hint that we're really on the right track. Okay, so now you might think that one of the next ones we talked about when we were just explicating the phi1 function was phi1 of omega naught, and we've explicitly disallowed that as a way to write beta, because I'm using omega naught there. But you'll remember we had this thing that we thought was a disappointment, which was phi1 of omega 1 omega naught is exactly the same number. It's exactly the same countable ordinal, countable tree ordinal. So let's just write it that way and use our rules with it written as an omega 1 here. Okay, so let's see what happens. If that's our beta, we're going to have that g beta of x is f of, we do two things. We extract that omega 1 and then we gx it. And remember, the gx of omega 1 is just omega naught. And so that's going to be f sub omega naught of x. Okay, so that's cool. We've found a very particular beta, namely, you can write it either way, but let's think about it this way, or you can realize that a little simpler way to think about it is this guy. Okay. And it's a beta such that the g at that level replicates f omega naught of x, which is getting moderately powerful. Okay, this is the precise version of something we did see before, which I claimed a while ago when we were sort of building out this story of getting bigger and bigger ordinals and looking at the g's, is that if you looked at the Veblen sub omega of 0, use that as the ordinal index for g and apply to x, you got approximately an f omega naught level function. Now we have a precise version of that, which I like. Okay. All right, what about the next one? The next one we looked at, I claimed that if you use alpha is omega 1 plus 1, suddenly you get something rather more powerful. Okay, so we're going to look at beta is this guy, phi 1 of omega plus 1, omega 1 plus 1, comma omega naught. So its reduction is, we're just going to take this sucker and gx it. Well, now remember what happened to gx. Gx of a successor is the successor of the gx, so the plus 1 just comes through, and the reduction of an omega 1 is omega naught. Okay, so that's our reduced version. Okay, and the exact result is that this very powerful beta that is of height gamma naught, one of our favorite ordinary ordinals, the g beta of that is something that gives you f omega naught plus 1. So notice how this is replicating two things. One is that specifically, if you look back to some other videos, g sub gamma naught, we said that that was approximately something on the level of f omega naught plus 1. Now that's been made an exact result. The other thing is that it still is telling you, the fact that g really is pretty reluctant to grow in a little bit of a backwards way. In order to create this beta such that the g strength of that was equivalent to f of just one more than omega naught, what did we have to do? We had to put in omega 1 plus 1 into this control argument. And what did that do? That meant iterate the phi1 with omega 1 argument many, many times. And that's what just blew up the strength of this ordinal to gamma naught. Okay. And so again, we're still at the stage, and it's going to be a little bit weird because very soon we're going to see the G and the F match up. We're still at the stage where we have to make this beta really big, a lot bigger, to just replicate adding 1, doing a successor on the F thing. Okay. But now let's use the real power. Okay, so let's set alpha is something that's actually itself constructed with a phi function. Okay, as I've said before, the 3 isn't essential, but it sort of starts out with a nice little booster step of an epsilon naught kind of construction, an iterated exponential construction. So we're going to do iterated exponentials basically in a clever, organized way on little omega 1 and to create something in big omega 2. And as we've said before, we use that as the control argument and omega naught as the main argument in the phi1 function to create beta. By definition, the collapse version of that, the C of that, is just extract the phi2 part, that control argument, and demote it using a gx. That's just phi1 of 3, that doesn't get changed, and omega naught. This is an omega 1. Haha, that was wrong. The omega 1 gets demoted into omega naught. Again, because of our rules for which things are allowed, this doesn't depend on x. Even though the C function is defined in terms of g sub x, this just turns out to be something that's independent of x, which is nice. Okay, and what do we get? Using this honking big ordinal, we get that g sub beta of x is f sub c of beta of x. And what does that translate to in terms of our previous understanding? Well, remember, this is something whose height is epsilon naught. It's actually, its height is exactly epsilon naught. And this sucker was much bigger. That sucker was something whose height is the Bachman-Howard ordinal. And it's really created in a very similar way to how we created the Bachman-Howard out of an ordinal collapsing function. We did some ordinary arithmetic to a bigger kind of ordinal, namely the first uncountable ordinal, and then we put that into a machine that is designed to create countable ordinals. It's just, I think, more elegant this way. Okay, so now we've got an exact version of something we had before, and that's about as far as we got last time. We didn't go beyond the Bachman-Howard ordinal, and still we're at the stage where to get G, a certain G to match a certain F, the ordinal argument of G has to be a bunch bigger than epsilon naught. Oh, sorry, this should not be a subscript. Okay. All right, but now we can put it all together. Okay. We had already defined this TOS sequence by saying, okay, start with just the ordinary number 3. Now phi1 with that as the argument, as the control argument, and omega naught. Okay. Now, instead of doing that at the phi1 level, do that at the phi2 level. Use that as the control argument of phi1. Okay, next version is use that at the phi3 level. Use that as the control argument for a phi2. Use that as the control argument for a phi1, etc. So tau n is a nested sequence of phis, and again, I've talked about how that uses bigger kinds of ordinals, qualitatively bigger ordinals, collapsing each stage essentially to create bigger and bigger countable ordinals. Okay, and this dovetails exactly with how G works. This is really the punchline of the whole thing, that if you do our collapse operation on, let's say, the n+1 version of this, okay, what that means is first extract all the stuff that's inside the phi1 function. Okay, that's this stuff up through an n+1, a phi n+1, and then gx it. And we know what gx does. It demotes every single one of those phis one stage. It demotes every one of the omega n's one stage. And guess what? We have phi1 of phi2 of phi3 up to phi n, not n+1 anymore, applied to the appropriate omega n minus 1, etc. That is exactly what we see as the definition of tau of n. So it's all, it's the whole, in Wehner's article, sort of the whole superstructure is designed to make this work. That we have this nested sequence of phis, and we have an operation that extracts something inside of phi1 and demotes it appropriately so that you just get the previous version of the nested definition. And that's what we wanted. We wanted a sequence of taus and a collapse operation such that when you collapse the next tau, you get the previous one, and such that a g of that next tau of x is the same thing as f of the previous tau applied to x. Okay, so there we go. that is what we wanted a while ago, like, I don't know, 10 videos ago or so. We've got a sequence, a chain, where the G's link exactly to the F's, but of the previous stage. So if that's as far as we went, we would still be saying, oh my gosh, you know what? The truth is, these taws, this taw, taw of n plus 1, is a much huger ordinal than this sucker, taw of n. And so we could say, it's still saying that the G's are really, really slow growing because you have to go to the next stage in this process to replicate the F. But the magic of taw, the magic of ordinals and things like that, is we now declare taw to be the tree ordinal with that fundamental sequence. Or in other words, taw is the function we've just specified from omega naught to omega 1. Okay. And then, exactly as we had in a few videos ago, g taw of n plus 1, well, let's write it out one more time. That's g sub taw of n plus 1, putting an n plus 1 in. Okay. But now we get to use the fact that that is an f of the previous taw. There we go. Of n plus 1. Oh, wait a minute. That's greater than f of that previous taw of n, which is f sub taw of n. Okay, so that last step is crucial if we want to have this process, this property of the g's and the f's coalescing, kind of interleaving with each other. You have to take the limit of this cool process, each stage of which, each finite stage of which, like taw of 7, is an immensely huge ordinal, and f sub taw of 7 of x is an immensely fast-growing function of x. But if you take the limit, because these have a very well-defined interleaving property, then you get that the g and the f kind of meld together. Okay, but remember, even if that's not what you came for, f sub taw itself is an unbelievably fast-growing function. And as I said before, you know, I always like to just go one more and say, let's say f sub taw plus 1 of 3, right? If you take that and you put in a 3, it's just ridiculous, because then you give yourself access to not just small versions of these ordinals to put into your f function. Oops, sorry. These guys here, you get access to these guys where the n itself, the number of times you iterate and nest the fees, is unbelievably large. Okay, so this is absolutely by far the biggest number that has appeared in these videos so far. We can get bigger, but using this really, really elegant technique, I think it's a little harder. I think it's a little hard. So speaking of elegance, boy, this is a long one, but let me just collect the essential things together. There's really not a lot here that you need. You don't even really need to know what a usual ordinal is. You just say, here's the definition of a tree ordinal. It has 0, it's closed under successors, it's closed under a generalized version of fundamental sequences, which are just plain old functions. Given a function from ordinals to themselves, here's how you iterate. The first two are pretty obvious, and the third is what you usually do with limits and fundamental sequences. Here's the phi functions, which are a straight up generalization of the fast growing hierarchy. Here's the tau sequence, just a nested version of the phis. And if you want to get your huge growing function, just say f sub tau of n is phi naught of the nth thing in the tau sequence as your countable ordinal, and n as your straight up input. And that is all you need to create these immensely ridiculously huge numbers. All right. One thing I want to mention, I think I've alluded to this before. We could have achieved a very similarly fast-growing function by taking the OCF story that we were talking about before. That's this Buchholz style. Oops, I think that's 2 H's. And instead of just using one new ordinal placeholder which we were using the least uncountable ordinal for. Just use a countable family of bigger and bigger uncountable ordinals. It's basically what we were doing here. But now that I've looked at this and written these videos up, I think it's cleaner for these purposes. What I think this doesn't do for you, I don't think it's a way to get a complete system of ordinal notations. For ordinal analysis and like the foundations of mathematics stuff, I think you really want something that gives you a way to write every single ordinal with no gaps. And that hasn't been the purpose here. And that might not be something you can use this for. Um, and also we've gone to the tree ordinals where we've declared the fundamental sequences to be paramount. And for a lot of purposes, those are considered extra data. So I don't want to say this completely supersedes what you'd see in a different presentation of ordinal collapsing functions, but basically it is a cool way to do those ordinal collapsing functions by, this is really the key, those 4 lines, by just pushing the idea of the fast-growing hierarchy as far as we can, and that's really cool. So that's it for this segment of these videos.